Bismillahirrahmanirrahim. This is Pakistan International School Taif. Dear students, this is the first year class grade 11 and we are talking about the lecture number 22 and subject chemistry and valence bond theory. Modern theories of covalent bonding we are talking about. And the last time we done the examples of hydrogen fluoride where the single covalent bonds are going to be formed. Now according to the valence bond theory, multiple bonds multiple bonds. So example is oxygen. This means oxygen atomic number 8 and electronic configuration is 1s2 2s2 2px 2py and 2pz 2px1 2py1 2pz1 and you are seeing 8 2 plus 2 there are 4 5 6 and 7. So now 2 and 2 4 5 6 7 and 8 and there are 2 unpaired electrons are here. This is one oxygen atom and second oxygen atom atomic number same 8 and same electronic configuration and this is a 1s 2 and this is a 2s2 and 100% same and this one is a 2px 2 electrons and according to rule we have to put in the lower spin, downward spin 2pz like this. So they are going to overlap with each other. You are seeing there are 2 unpaired, so they are overlapping like this. Unpaired electrons, they are going to overlap. So first bond is formed a single sigma bond and single covalent bond, and second bond is called a double covalent bond and we call pi bond. So there is a sigma bond and pi bond between oxygen and oxygen atom. This is the structure of oxygen. If you want to draw the structures, so like this. This is the oxygen and this is 2pz, 2py and 2px like this. So this is a 2pz and this one is a 2py and 2px. This is for one oxygen. So if we are going to overlap with another oxygen, so students, 1p is filled. These are degenerated orbitals. Don't say x, y, z. This is only for identification coordinates. But there are p orbitals, and all they have the same energy. Degenerate orbitals. That's why x and x they are going to overlap. This is another oxygen. This is another oxygen. There is a sigma bond straight overlapping. Already we done this. So 2px. There is a sigma bond like this, and this is a 2pz for another oxygen, and 2pz and 2pz to form a pi bond, and pi bond is formed by the parallel overlapping between going to be filled, so we shed. This is not participate. See this one. Like this. This is not going to participate. Only P to form a pi bond, and this P and P is going to form a sigma bond. So double covalent bond is formed, sigma bond and pi bond, and this is the filled one, which is not participating. And you can see in the example that only two are going to participate and one is not going to participate. And these are all p orbitals, and they are degenerated. Their energy is the same. So each oxygen atom has two filled 2p orbitals. In the valence shell, on the basis of valence bond theory, two covalent bonds can be formed between two oxygen atoms. One is a sigma bond and other is a pi bond. One bond is end-to-end overlapping. Yes, there is an end-to-end overlapping to form a sigma bond. And other one is a side-to-side overlapping, side-to-side, above and below. This is called a pi bond. So this gives a pi bond. Thus the double bond is formed between oxygen and oxygen. Remember, in multiple bonds formation of first the sigma bond is formed. Secondly, pi bond is formed. We done many times in the previous lectures that first bond is formed between the two atoms is called sigma bond. Other bonds are called pi bond. So dear students, this is structure of oxygen. Structure of oxygen. Double covalent bond, and this is also you have to note it very well in your book. See your book and also copies, write down. And this chapter number 3 continue. Chapter number 3 continue. And now I am going to omit this. Now, other example for multiple bond. Nitrogen. Nitrogen has triple covalent bond, one sigma bond and two pi bonds. There are three unpaired electrons if you see nitrogen. So students, starting from here, nitrogen, atomic number is 7. Atomic number is 7. So 1s. 2s again 2 and 2px 1 2py 1 and 2pz also 1. All three are unpaired, so means three bonds will be formed. According to valence bond theory, the partially filled atomic orbitals participate in the bond formation. So you are seeing this one. Three are unpaired in the one nitrogen atom, and also if you write for the second nitrogen, atomic number is 7. Again same electronic configuration. 1s 2s 2 like this one, 2px 1 2py 1 and 2pz also 1. So all the three unpaired electrons participate. All the three unpaired electrons participate in the bond formation because they are all unpaired. So that is why you can find triple covalent bond between nitrogen and nitrogen atom. One is a sigma bond, two are pi bonds. one is a sigma bond and two or pi bonds are going to form in the nitrogen atom. According to the valence bond theory, chapter number 3rd, valence bond theory. So structure I already told you for the oxygen. So same. Here is a nitrogen. This is a 2pz above and below. Dumbbell shape nitrogen atom in between. 2pz. This is a 2px. This is a 2px, and this is a 2py. 2py. This is for one nitrogen. This is for one nitrogen, and therefore another nitrogen seen like this one. This is the one second nitrogen, and this is a 2px. 2px for the second nitrogen, and they are the end-to-end overlapping to form a sigma bond. And this is a 2pz, and 2pz and 2pz, because this is also unpaired, so they are going to form a 1 pi bond, this like this one, and this is a 2py, 2py. So this y and y, they are going to be overlapping with each other to form another pi bond. So all the three unpaired electrons participate to formation of the bonding. End to end, straight overlapping, one end of the 2px and one end of the other 2px for both nitrogen to form a sigma bond. And parallel sideways overlapping between 2pz and 2pz, the gap between them are not as stronger as compared to sigma bond. So they are one pi bond and the other pi bond. This is the structure of nitrogen. So dear students, this is a structure of nitrogen to form a triple covalent bond according to valence bond theory. Three half-filled p orbitals are present. Nitrogen atom approaches each other. Their 2px undergo end-to-end overlap to form a sigma bond, and other 2p orbitals z and y, they are parallel overlap or side-to-side overlap to give a pi bonds. Now there are 5 distinct regions of electron charge density in the nitrogen molecule. The sigma electrons between the nuclei to form a sigma bond. The pi electrons above and below, pi electrons. The sigma electrons form pi bond. The pi electrons in front of and behind the sigma electrons from another pi bonds. This is confirmed. This is confirmed that oxygen has a triple covalent bond. One of them is a sigma bond and two are pi bonds. So dear students, you have to draw this one, write each and everything in your copy. This is also important, may become an examination as a short question. Then actual valence bond theory hybridization approach is going to start now. Write this one. Multiple bonds, triple covalent bond between nitrogen and nitrogen, how it's going to be formed. You have to draw this, write down each and everything. Now, students, there is a very important topic to be start, and actual the valence bond theory is starting here to draw the structure of different covalent molecules, and we call hybridization. Hybridization definition is when two or more than two atomic orbitals after intermixing to form same set equivalent of Hubbard orbitals having same energy and same shape are called hybridized atomic orbitals, and the process is called hybridization. And you can find this definition which is given in your book. I'm going to read this. The process of mixing of atomic orbitals. They may have a different energy. One is a S and other is a P. Shapes. You will get a new set of equivalent, same energy and same shape orbitals you will find are called hybridized atomic orbital, and the orbital process is called hybridization. Now students, here we will talk about three kinds of hybridization. Number one is sp3 hybridization, 1:3. Second, sp2 hybridization, 1:2. And third is a sp hybridization. The ratio is a 1:1. So as we proceed, the S character is going to be increased and P character is going to be decreased. Here 75%, 25%. Here 66.66% and 23.33%. Here 50% character. So as we proceed, the S character percentage is going to be increased and the P character percentage is going to be decreased. We will discuss. So before starting the hybridization approach, just I am going to explain, and you done in the previous chapter when you done the electronic configuration, and I told you that valence number topic is given in the last, if you see. Valence number is going to be formed according to the valence electrons, number of electrons in the valence shell. And I told you carbon is not going to follow this one. Carbon is not going to be followed. The reason, because here carbon is atomic number 6. 1s2, 2s2, 2px1, 2py1 and 2pz0. This is. So according to this electronic configuration, you can see here there are only 2 electrons which are partially filled. So according to the valence bond theory approach, as you done before, the examples of oxygen, nitrogen, hydrogen, chlorine, fluorine, hydrogen fluoride, whatever it is. So these unpaired electrons participate to form a bond. Carbon has 2 unpaired, so 2 bonds can be formed by the carbon. So carbon should be divalent. But carbon is not a divalent, carbon is a tetravalent. 4. Carbon has a 4 oxidation number, 4 valence, not 2. So that is why we are not going to follow the previous formation of bonding as nitrogen, oxygen, hydrogen, fluorine like this one. Because valency of carbon is 4, not 2. Which is given in your book introduction. If you see the hybridization of atomic orbitals. Carbon has a two filled orbitals according to its electronic configuration, and also not only for the carbon, you can see for the beryllium atomic number is 4, 1s2 and 2s2. So there are no unpaired. Cation is complete with the s, and also 2s is a filled one. There is no partially filled. So according to the previous bond formation, so beryllium should not form the bond. There is no bonding should be in the beryllium. But there are compounds divalent. Beryllium is divalent. So there is same for boron also. So due to this reason, the previous practice we done, bond formation of other molecules, is not applicable. So that's why the new approach is going to be studied here, hybridization of atomic orbitals. Examples are given here. The scientists Pauling and Slaughter resolved this discrepancy by the introducing of concept of atomic orbitals. Pauling and Slaughter, which involves mixing, I told you, definition, mixing of pure atomic orbitals, mixing, and to give a new set of atomic orbitals. So during this process, according to this concept, the orbitals differ slightly in energy, intermix to form new orbitals called hybrid orbitals, which differ from the parent atom. Parent atomic orbital differ from the parent atomic orbital. Shape and energy possess specific geometry. It also gives satisfactory explanation of valence bond, valency of an element also, as there are drawbacks already I told you here. So in this process the electron belongs to ground state, so I am going to explain here. So students, there is a discrepancy here. There is no bond formation or no complete bond formation. Valence is not going to be satisfied by these ones. So one by one I am going to explain here, students. sp3 hybridization. In the sp3 hybridization, the process in which one s atomic orbital, ratio 1:3, one s atomic orbital intermixes with the 3p atomic orbitals to give equivalent, same number, same energy, 4 hybridized atomic orbitals. 4 hybridized atomic orbital is called 4sp3 hybridization. So according to definition which is given in your book, you can see in the sp3 hybridization, you have to open the valence bond 3 hybridization of atomic orbitals. The process of mixing 1s, as I told you, orbital and 3 orbitals to form 4 new equivalent sp3 hybridized atomic orbital is called sp3 hybridization. And in the sp3 hybridization, the very important examples are, the very common example is methane, maybe other also, but this is a common, methane, and then ammonia. This is also for the sp3, and water. These are the 3 examples in sp3 hybridization. Now if you see the sp3 hybridization, I am going to explain methane. Carbon is a central atom, nitrogen is central atom, oxygen is central atom, which involve for the bond formation. So carbon atomic number is 6. Electronic configuration 1s2. 2s2. 2px1, 2py1, 2pz0. This is the electronic configuration of the carbon, and this is the actual electronic configuration we call ground state. This is called ground state. And this will not help us to form the tetravalency of carbon. So as I read from your book, there is a promotion of electron. So this is the carbon 6, second step. This is same. 1s, 2, and there will be a promotion of the electron. From the 2s, one electron is promoted in the 2pz. So 2px, 2py, and 2pz. So one electron is, you must write, promoted from 2s to 2pz. Now you can find 1, 2, 3 and 4 half-filled atomic orbitals, 2s1, 2px1, 2py1 and 2pz1. Students, maybe the question asked that you are promoting electron from 2s to pz. So from where you need energy? From where this energy come to promote electron from 2s to 2pz? We need energy. The energy is compensation is like this because already 2 partially filled orbitals are there and they can form bonds. So when they are going to form bond, the amount of energy is released. So this amount of energy is released, compensation of energy to promote 2s to pz. So there is a compensation of the energy, and this state is called excited state. This state is called excited state. Now hybridization. Already I told you the definition of hybridization. 1s is complete, K share is complete, no need for this. Intermixing. There is a intermixing of atomic orbitals. S1 and P3. There is a mixing, means plus. So 2s1 plus 2px1 plus 2py1 plus 2pz1. They are going to intermix. There is a intermixing. Intermixing of atomic orbitals. 1, 2, 3, 4 with 1 and 3 ratio. Atomic orbitals, they are intermixing with each other to form equivalent 4 sp3. This is the one. second, third, and fourth. There are 4 sp3 hybridized atomic orbital, 1, 2, 3, and 4 equivalent, 100% same. Dear students, there the one thing, the diagram is not given in your book. Intermixing diagram is not given in your book. I am going to draw here. You must write in your copy, and with a small page you have to write and attach with your book where the topic is. So I am going to how they are intermixing 2s. This is a shape of S, you done? 2s, one like this one. The shape of S, spherical, plus 2px. This is a shape of 2px. 1 plus 2py. This is a shape of 2py. 1 and 2pz. This is a shape of 2pz. This is also 1. So they are going to intermix. This is not given in your book. Please draw in your book if you find space, or not. Draw in your copy, and other also draw some small page, and you have to straighten with your book. 2s1, 2px1, 2py1, 2pz1, they are intermixing, plus, plus, plus. Now after intermixing, you will get equivalent 1, 2, 3, 4 hybridized atomic orbital. According to your book, the shape of hybridized atomic orbital is like this: small lobe and big. This is the shape of hybridized atomic orbital. Same shape for all. If you have a sp2 hybridized atomic, same shape. If you have a sp hybridization, same shape. The shape of hybridized atomic orbital is the same. Now you have a 4 equivalent same. So dear students, now if I am going to draw the structure, for the sake of simplicity, according to the book, there is no need for drawing this small lobe. This small lobe, don't draw. In some books, like this one is given, like this one. But if you don't draw this, okay. So this is the one sp3. They are 4 tetrahedron at 4 corners. 4 corners. And the velocity of carbon is 4. 1, 2, 3, 4. And it is going to be explained that carbon is not a divalent according to this electronic configuration, but carbon is a tetravalent according to hybridization approach, and there is an end-to-end overlapping 1s1 for the hydrogen to form sigma bond 1, and there is an end-to-end overlapping with the 1s1 of the hydrogen. You will get another sigma bond, and likewise all 4 sigma bonds are formed between the hybridized atomic orbitals and 1s1 for the hydrogen. Like this. So 4 sigma bonds. At 4 corners, tetrahedral corners, 4. Well, this is the structure of BZN done in the Vesper theory. So if you draw like this one, here, 1 hydrogen, second hydrogen, third hydrogen, fourth hydrogen. 4 4 corners, 4 valence, 4 valence number. Like this one. So angle is 109.5 degree, and the name of this shape is a regular tetrahedral. Regular tetrahedral shape of the methane. So students, this is the hybridization approach, and very important. Write the explanation, whatever the electron configuration involved, and also draw the structures must, and reason why the carbon is not a divalent and it is as a tetravalent according to the hybridization approach, and sp3 hybridization involved in the carbon. Write down, and also you have to reproduce same, and must draw this, because in the examination you have to draw how there is a mixing of the atomic orbitals s, px, py and pz, 25 percentage, and there it is a formation. So dear students, here we are going to stop. Thank you very much. Then we will start another one.